Hello everyone, this is the video lecture for Math 1325, Business Calculus, section 12.4. We're doing the definite integral. So what is the definite integral? Let's just start with that. So what we had been doing are integrals that kind of looked like this here. And we would say, oh, you add 1 to the power, and you divide by the new power, and then we put a plus c. And we're like, yay, we're done. That was it. What we're going to do now is essentially going from a number to a different number. So here in this case, from 4 to 5 of what we just had. So let me show you how this works on just a simple one right here. What's going to happen is that we still take our integral, but instead of saying a plus c, we then do this vertical line and say from 4 to 5. This vertical line means when, like when something happens or something like that, or when x is from 4 to 5, that kind of thing, or such that, a little st for such that. So either way, basically what we're going to do is then plug in those numbers into the x like this. So you got a 5 cubed all over 3, and then we're going to subtract and put the 4 cubed over 3. And so, of course, we're going to get an answer. And, hey, look, there's Desmos. We got that open right now. And let's... Aha. And bloop, we got an answer. 61 over 3. Cool. There it is. We just did that integral. Yay. So what does this mean? Like, what are we actually doing here, like in reality, I guess you could say? With a cubic, it kind of looks like this. But again, we're only focused right here. Say this is 4 and say this is 5. So we found the area underneath the curve between 4 and 5. So we found the area right there, which again, if you saw the decimal, it was like around 20.33 or something like that, right? 20.33. So that's the area that we just found. This is the area underneath the curve. Cool. Well, that sounds awesome. I'm going to say that we have a formula here, and this is called the fundamental theorem of calculus. So it's got to be pretty important. And so here it is. We got integral from a to b of f of x dx is equal to capital F at b minus capital F at a, or of a. And that's it. So what's going on here is that this capital F is essentially the integral. So it's going from the square to the cube and all that kind of stuff. And we're plugging them in, and you just subtract. The reason why we subtract is because we don't want to have, like, basically the 4 is all this area here, and the 5 is the entire thing. So we're like removing this part from this triangle-y looking area. That's all it's doing. So all of this is really cool. It's super fun and easy. And yet, it is not what we're doing today. What? Why are we not doing that, Chad? Because this section wants you to do it with rectangles. Let me demonstrate. So let's say we have the same cubic, and we're going from 4 to 5, and I'm like definitely exaggerating here. What they're saying now is that we should use little rectangles, and we're going to add all the rectangles together, all the little areas, and then we should get an answer. But what you're going to find is that there's inaccuracies here. And I'm going to try to redraw this and show you what's going on. So if I did this style here, you see how we're overshooting it by a little bit. Okay. Another version, very similar to that. Just doing the same kind of curve here. What if we did this type of rectangle, and you could see that we're going to undershoot it a little bit. And finally, there is another version which does something like this, and I'm making them really big so you can kind of see what I'm trying to do here. So this one has a little bit over and a little bit under, and so maybe they equal out a little bit in the end. Well, all these different types have names, and I know that I don't draw them super well, but this one here, it's actually called left, and this one's called right, and this one's called midpoint. And so let me draw a little name for that. So this is right, this is called left, and this is called midpoint. What's going on? I guess I could spell the whole word out here. Midpoint. what's going on is that we're deciding what side to choose as the height of the rectangle. So let's say we're doing a left. So I start with a height, and then I'm going to head towards, I guess, to the right. So it's on the left side that it's determining the height. And so here on the left side of the rectangle is its height. And left side, and the left side. Again, of this little rectangle we just have right here, it's the left side that's touching the graph, essentially. And that's why it's called left. But I head towards the right, so it's like it's equal to that left side there. Anyways, we're going to do a lot of this kind of stuff, and it is more numeric than what you're seeing here often. Something else that you're going to be seeing at least a little bit is Riemann sums. And let me just give you like a synopsis of this, like super fast, a little summary. So I got S sub n. S stands for a sum, like summation. And then we got this sigma thingy, which I'm going to make it actually look good for once in my life here. Give me a second to do this right here. There we go. So that's a capital sigma. It again means sum. And we got k equals 1 all the way to n of f of c sub k, and then times delta x. And if all of this looks very strange to you, it is. And really, we're here in this class, we should not be focusing too much on these little details, but we're going to get through it. What this really is the integral of f of x dx. And do you see it has the similarities? This here is like a big S. Again, an S here. F, and then it's kind of like an x value, let's just say. And then dx, delta x. You see how that's d delta? That is a little delta. I don't know if you noticed that. That's a Greek for change, same as a d, blah, blah, blah. Okay, so I have a note here on my notes. It says that this section has a whole lot of multiple choice, and I remember going through it kind of recently, and there is a lot of multiple choice, and I'm not going to be covering a lot of those here in the video, but I do want to talk about the numeric side of things because it is a little tricky at times, okay? So what we're doing, again, is we want to do this, but we can't yet. That's going to be the next section, okay? Instead, we're going to be doing this, and maybe that a little bit. So here we go. 12, 4, 21. So I have, it says L3 is equal to 22, and we have R3 is equal to 16, and they say compute the error. Compute the error. What? That's why you watch these videos. Actually, whoa. I made a mistake. I'm so sorry. I was actually looking at part B. This is not a 16. This is a 29. Part B has this here. There you go. So that, and we're going to just compute the error again. Oops. Sorry. I was looking at the wrong place. Okay. So yeah, it says compute the error. Huh? What is that? It's very, very simple. You're simply going to just subtract them. And they want the positive values, so you know the bigger one goes first and all that kind of stuff. You could say absolute value if you want to. That is a perfectly fine way of doing it. Is this just also a 7? Look at that. I guess they're the same number this time. Whatever. Not every time, I would say not every time. But essentially, they just want a positive value for that. Very simple, very simple. What they're trying to say is that we have one that's over and one that's under. Here we have my right, which is over in this particular case, and left, which is under in this particular case. So what's the difference between them, essentially? Not always the left is bigger. Not always the right is bigger. It kind of just depends. You can see here we got the right one's the bigger one, and here the right one's the smaller one. It doesn't matter, honestly. It just depends on the curve. So we have 25. So f of x is equal to 23 minus 3x squared. And they say they want to partition a 0 to 12 interval into 4 subintervals, subintervals. Okay. And sec sub k, This is totally everything you should totally know already, right? Right? No, I'm joking. I'm totally joking. Seriously. That's why you're watching videos, and that's why I'm explaining them. So that's a x with a k minus 1 subscript, and then that's a x with a sub k, and then all this stuff divided by 3. And they say, find S4. Like, I gotta say, this is seriously the most cryptic thing in the whole wide world. And that's why I do the videos. Obviously, would I leave this, like, all right, go on. You got this, guys. Or hey, you know what would be awesome? Go ahead and read the book. Yeah, yeah, that sounds like a great idea, Chad. No, none of that. So let me show you what's going on. Again, once I start doing it, you'll see the pattern. It's not that bad in the end. And so first off, we got to find out what this partitioning into 4 subintervals looks like. And so we're going from 0 all the way to 12, and we want 4 subintervals. And really, we're just saying this 12 divided by 4 is 3. And so we go 3, 6, 9, 12. You can see we got 1, 2, 3, 4 little subintervals, kind of like they're going to be like rectangles, essentially. And I don't know how high or low or whatever. That's not the point here. But you can see that I made 4 little sections. And now what we're going to do is plug in this as an x value. Okay, this is kind of like going to be an x value-ish. So I know this is just strange. So how do we do this thing? First off, we need to find out what our previous and then what our current values would be. Another way to think about it would be this is the left side of the rectangle and the right side of the rectangle. Well, just like looking at this first rectangle here, that's going to be the 0 and the 3. So we put a 0 there and a 3 there, and we knock it out and get an answer. Okay, so here we go. Let's start working it. So C1 would be then 2 times 0 plus 3, and then all divided by 3. Now, again, I put 0 and 3 in. Later, we're going to get some other numbers. This is actually pretty easy because the 0 goes away. 3 over 3 is a 1. So hang on to that for a minute. We're going to use it, but my notes are actually kind of more disjoint. I want to do it all at once here so you can see the pattern better. So I'm going to start with a 3, and then I'm going to go to a 6, divide by 3. So that's 6 plus 6 is 12, divided by 3 is a 4. And so that we're going to use that here again in a second. All these are supposed to be x values, kind of. It's actually, if you want to know the real theory, it's where the curve is touching. So here at 1, it'll be here at 4. We're going to figure out where the other guys are touching. And this is supposed to make it more accurate, I suppose. But really, this is such high theory that I don't even know if we do this like for realsies, in our Calculus 1 class. Like, we do it a little bit. I know we do, obviously, because it's actually a topic, but boy, let me tell you, is it really worth it, though? Like in this class is what I'm kind of getting at here. But that's why we're doing it here together, because there's no way I'm going to leave you hanging. Oops, I wanted to answer divided by 3. There you go, 10. So if you can see, there's actually a pattern here, and I would say that does not happen all the time. Don't just expect it to happen. But yeah, 7 and 10, and this is kind of like where the curve is going to hit, essentially. Okay, whatever. So I'm going to take these x values. These are all x values, and I'm going to plug them in to my f of x right here. Okay, so basically I have f of 1. I'm going to have f of 4, I'm going to have f of 7, and then I'm going to have f of 10. And again, my f of x was, since I have Desmos up here, that was a 23 minus 3x squared. And you can do that kind of thing here in Desmos, where you just say x equals 1, and you get an answer. It's actually very fast and easy. So plugging in the 4, the 7, and then the 10. Okay, awesome. So we have all our numbers. Now what do we do with these things? We add them all up. It said S4, sum of the 4. And so we're going to add all these things up. So here we go. I'm going to add them all up. Add them up. And so let's do that here. Oh, we're not quite done. I was just about to say, hey, we got it, but I went and looked at my paper because this is a pretty detailed one. That looks great. Yay! And that is not the final answer yet. So what we're doing here is we actually need to find the area. And so what we did is we found all the heights, okay, and we added up all our heights. But really what we also need to do is multiply by our widths. And the reason why is because we're looking for an area of a rectangle, okay? So area of a rectangle is length times width. And so our lengths were all these other numbers. So that would be the 20, the 25, the 124, and the 277. But then my width, again, for all of them, was a 3. So I need to take all these that I just found and say times 3. Now, I know that we got negatives, and what's happening here is that they're like below the x-axis, and they get like more and more negative. So the curve is like doing that. Don't overthink that. We just have this thing. And then I say finally times 3. And this is my final answer. Again, I had that on my notebook. So answer times 3, and there you go. Okay, cool. This is your final total integral area thingy for this. Now, I know it's a negative area. Just, again, it's below the x-axis. That's all. Wow. That was a lot just for this. One question, and that's fine. That's fine. That's why we're here. So let's keep cruising, keep moving. Let's lock in. So here we go. I have another function, and they say that we're going from 0 to 9. It's supposed to be a 9. Okay. And they give me the C value. So C1 is 1.6. C2 is 4.5. C3 is 7.3. And they say find S3. It's the work is kind of done for us already a little bit. So what we're going to do is we're going to plug these values in and get a whole bunch of numbers. And then we're going to add them all up and divide by, multiply by 3. And the reason why 3 is because my interval is 0 to 9, and I'm wanting to cut it up into 3 sub-intervals. So 0, 9, and how would I do that? It would be a 3 and a 6 and a 9, 1, 2, 3 different rectangles. You could see something like that. And so the width of each one of these rectangles is a 3. So that's my width. Again, this is my length. This is my width. So let's do it. So I'm going to start over, essentially. X squared minus 7x minus 30, and start plugging in my x values. Oh, that's a 30. Fraction. Yeah, I don't. So I have fractions for my answer, and I don't know, I can't remember if my math lab wanted it as a fraction or not in the end. But it would be safe to have a fraction because then you could just convert it to a decimal if you have to. Okay. And yes, again, we're getting negatives. And I know that it's honestly not a really good intro demo of what this is and why we're doing it. It's actually it's actually pretty sad, honestly. But in the end, we're not focused on that. We're focused on getting the answer, and that's okay. So here we go. Again, plus a negative or just minus. And there we go. So fraction, negative 3231 all over 10. How is this helpful in business? I can't tell you right now, honestly. But there are a couple questions at the end that are really legitimately awesome. And they are applications to what you do. And that would be good. Just right now, the homework is just set up to be this way. And that's not on me, man. I didn't make the homework. So let's keep going. We have this graph on this problem. And the graph, it's a cubic, so it's going to do this thingy here and like that. And what I want to do is give you some colors because it's going to be a little bit more colorful. Let's start with some like more pinky kind of stuff here. And they have this like pink area, let's just say. It's a really dark pink. Okay. I don't know. What would you call that? It's not a red. I don't know. It's just a dark pink. Let's do some other colors. So let's do like a purple. That's pretty dark purple. Let's do a light purple. So we got light purple. Okay, that's a medium purple. Or like a lavender maybe. That's close enough. Okay, let's do some more. Let's go with, what would you call that? A teal maybe? It's darker teal. Not teal. Cyan? Yeah, I don't think teal. Teal's a little bit more green. It's more blue. It's like a dark sky. Let's call it Stormy Day. I'm making up names for this stuff. That's more of like a teal. There we go. And then here, that's a teal color. There you go. Okay. I know that I'm just trying to make up what it kind of looks like on the homework. It's definitely, I don't know. It's not perfect, but it's going to be what it is. Oh, great. Our connection has failed. Let me fix that by just getting rid of it. So you'll see it come back up. Sorry about that. So here we go now. Let's try to figure this thing out. So they give us all these letters for all these places, and they call this one A. They call this one B, like literally like the edges here. Here, that's going to be a 0, obviously, and then this is 0. Let me make it look a little bit more like 0. And then this is a C, and this is a D. Okay, cool. And then they give us capital letters for all of these different areas. That's A, B, C, and D. Try to make that a little bit better looking. D. Okay, cool. So we got all that. And then they say that A is equal to 1.399, B is equal to 2.635, C is equal to 5.749, and D is equal to 1.834. Awesome. And then they say, hey, find the integral from 0 to C of f of x dx. Okay. So they're saying from 0 all the way to C. They're saying from this 0 all the way until C. So they want this area right here. So that's going to be equal to that C area, which we already found was a 5.749. And we're done. That was it. That whole problem, all my coloring, all the cool names we came up with, just, it's that one. Okay. Yeah, I'm not kidding you. We're done. But let's just say, I don't think this is going to happen, but let's just say the homework gets like more difficult, I guess. Let's go instead from little b to little c for just a second so I could demo kind of like what they're trying to get at. So they're wanting this one and that one, kinda. The problem is that this is negative. This is a negative, and this is a positive. And I need to put them together. So I wanted to put those two together, but I don't literally add them. I have to say a negative 2 and then a positive 5. And so I don't actually have an answer for this because I didn't do it on my paper because it's not really on the homework. But there we go. 3.114. Sweet. And yeah, that, I don't know. At least we named some colors. That was pretty cool. I think we had a good time there together. You know what I mean? Yeah. Oh, yet another one. I meant, no, this is a great problem. Okay. Oh, no. Hold on. They actually give you the function. So, That just makes it more insulting here in a second, honestly. So, okay. They say that we need to use these other integrals that they came up with. Like, bro, okay, there we go. Now we can draw on it. So they have an integral from 2 to 4 of x squared dx is equal to 56 over 3. And then I have integral of 4 to 5 of x squared dx is equal to 61.3. That's good enough. That's good enough. I don't really care. So they say, hey, use these to figure this out. Well, notice we're going from 2 to 5, so that means we're going from 2 to 4 and 4 to 5. So we're going to add these together. But notice that also that's a 1 in the front, right? And we have a 3 in the front. And so we're just going to say whatever we had here times 3. So 3 times, and then we have the 56 over 3 plus the 61 over 3. And let's go and do that right quick. And you'll see why I called it insulting here in just a second. Yep, that's fantastic. Look at that. Okay, because Desmos graphing has the ability to do any of these integrals for you automatically. So why did we have to go through all this pain of thinking at all when we could have just done it? Heck, if I wanted to do it by hand, that would be actually probably easier. So, I mean, the 3 stays in the front. We got cube and then over 3, 2 to 5. And so the 3's are going to cancel. I'm going to take the 5 and plug it in. So then we get a 5 cubed. Plug in the 2, so minus 2 cubed. And so, like, just doing this by hand, I mean, it's even easier than trying to think about what are you trying to say with all this other stuff. Like, I mean, so I did it by hand. I did it with Desmos graphing, or I could do it the way they tell me to do it, and that's kind of meh. It's okay, guys. It's okay. It's okay. We're gonna keep going. Okay, lock in, man. Lock in. So to be honest, this one here is approaching a good problem. It's not there yet. It's just not there yet. It's approaching it. It's getting close. Maybe. Probably not. Yeah, that's just part of it, man. Are there ever times where your boss is going to tell you, hey, you need to do this, or fill out this report, or do this paperwork, or blah, 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 and you're not going to like it, and you're going to think it's pointless to do, and all that kind of stuff? And yet, you're going to do it anyways because you want to not lose your job. And I guess this is a good test of stamina, at least that. So, yay. That's what we're doing here. So they give us this table, and they said that to use the left end, they have that in like the words of the problem. And that basically just means we're going to be excluding the last one for what we're trying to find out here. So to find the area, essentially I'm going to take all of my x values and add them together. I'm sorry, my y values, and add them together. And I want to multiply by the width. So how much is my width for each one of these rectangles? Is it 100? Calculator. I'm not going to waste my time. I'm not going to waste your time. This is the answer. I just got it in Desmos, essentially. All right, cool. That was awesome. And then they're going to ask for something else. And so this is the part B, I guess you could say. It says the error bound for estimate. The error bound for the estimate. And they provide this crazy formula, which, of course, you totally saw at some point, right? Because you totally read the book. I'm just joking. I'm just joking. Okay, here we go. Yeah, awesome formula, man. Hey, Chad, what do you mean by that? Well, it means that we're going to be finding the I think it's the last one and the first one, and then we're going to find out like the width between them and all that kind of stuff. This here, let me just show you. So that one that you totally got rid of, we're going to actually use it here. And so we got the 287 minus 0. Again, that's my guy right there. So those are my two f values, my two y values there. And I'm going to multiply it by my x values in those locations. And so that would be a 500 and a 0. So I got 500 minus 0. And all of that stuff there divided by 5, because we're going to have 5 rectangles. 1, 2, 3, 4, 5 rectangles. So 5. Calculator once again. And I'm just going to go ahead and get it for you. So it's 28,700. And you can see that answer by just looking at it. You get a 100 times that, and there you go. In my math lab, do not put commas. Do not put commas in my math lab. They're going to freak out. They're going to say, no, you can't put commas. I'm using them because we're humans, and humans need to use them. Okay, keep going. It says, find the number of subintervals. No. Not subintervals this time. Nope, it's subdivisions. My bad. N greater than or equal to, and then they have a box, so that the error does not exceed 2,500. Okay. So we have to go back to our error formula. And essentially we have like a y2 minus y1. And then I'm going to do my x2 minus x1 all over n. And they're saying that it's basically 2,500 that we're going to be working with here. Now, all of these we have, they're just wanting to find n. So that would be the 287. And then we have a 0. Here we have the 500, and then we have a 0. And then it's all divided by n. So to get the answer, it's actually going to be pretty simple. I'm going to take the n and multiply it over here, and take the 2,500 and divide it to the other side. So we get the 287 times 500 all over 2,500, and that's going to be equal to my n. This one I'll actually put in to Desmos. Notice that the fraction looks kind of weird here. It doesn't matter. It's all being multiplied and divided. So I got 57.4. And I believe you just... Okay, I would have gone up one, but maybe I'm misunderstanding it. Regardless, just 57. There you go. It should be an integer. That one I can at least say it should be an integer. So maybe they just rounded. So if, let's just say that you had like a 6 here, like a 57.6, let's just say, and they said 58, and then they just rounded. But if they said 57, then they're doing it because of this whole greater than kind of business here. I wouldn't think too much into it. It's not really worth your time. Just, go ahead and get an integer. They want an integer, okay? Because it's like how many actual rectangles, and, well, you need a whole number of rectangles to do it. 2471. Yeah, so that's x to the x dx, and they say this is equal to L sub n plus or minus 0.8, and you can right here, you can see just how business application wise this problem is. I mean, it's clearly made just for you. What? No, it's not. But I'm not going to shy away from the questions that are on the homework. I don't want to leave you hanging here. So they want, how large should n be in order to achieve this error? What do they mean by that? What they're trying to say is that 0.8 is my error, and this is just the answer, I guess. Okay. Well, how are we going to do this problem here? Well, it's not hard. We're going to do the same formula. So I got my 0.8 is equal to, and then absolute value of my y values. And notice that they're going to go from 1 to 3. So I'm literally plugging that in. So I'm going to 3 to the 3 minus 1 to the 1. And then all this times 3 minus 1 all over n. I mean, they just said how big should n be. So the reason why I'm doing 3 to the 3 and 1 to the 1 is because of this formula right here. You can see it's x to the x. So I'm just literally taking the 1 and plugging it in, and 3 plugging it in, and let's see what we get. Well, 3 cubed is 27, and 1 to the 1 is a 1, and we're having a 2 over the n equals the 0.8. Just like last time, what we do is the n is going to be multiplied over here and the 0.8 divided. Okay, so then I have n is equal to, this would be a 26 times the 2 all over 0.8. Let's go and do that. And I got a 65 straight up, and they wanted an integer, so they get an integer. There you go. Ah, finally. There's one last question I have, and this is actually legitimately good, and it's useful to business, I guess, in a little way. But give me a minute to kind of like explain it and get through it a little bit. There's still a lot of hoo-ha going on in this problem, where it really takes something that used to be beautiful and make it terrible. So let me just finish this up right quick and try to explain how to do the problem, and then I'll explain to you why it is, or at least used to be, important to you. That's a 65? Yeah, okay. You know what? You're not going to be able to read all these, so what I'm going to do is write kind of like sideways in a way. I'm going to do this, and then my 0.8, and here I got a 0.75, and then I got a 0.65, 0.61, 0.54, 0.48, not that it's going to matter here in a second, and then finally the 0.44. Okay, so they give us this table, and that is an A prime, meaning like area and then prime, so it's a derivative, and so when we integrate it, we're actually going to get my area. Anyways, they say find L5, and then they say find R5. So L5 is on the left side. Oh, I guess we are going to use the other numbers. No, we're not. No, we're not. No, we're not. Well, that's kind of Anyways, L5. So not just because it's on the left, but because the problem kind of talks about it a little bit, but they're wanting only to use these numbers right here. So it's not just because they're on the left, it's because they just say, hey, we're only going from 0 to 5 or whatever. Just kind of read the problem if you really want to, maybe. And to be able to do this one, it's very simple. So we're going to first say, what's the width between each one of these is a 1. And then I'm going to multiply that by the addition of all my stuff here. And the problem is that I need only 5 of them. 5. 1, 2, 3, 4, 5. Because I'm wanting, out of these here, I'm wanting the ones on the left side. So if this goes way back to rectangles like this kind of thing, and I'm using the left side for my curve and stuff. And so that's kind of what they're going with. So these are going to be defining what the rectangle's height are for the left side. Put it all into Desmos. I'm not going to waste your time there. Just there's your answer. Now they say find the right 5. So I'm going to use a different color since it's like near the end anyways here. Let's go back to, let's use that. So we're going to now use these here on the right side. Again, the equivalent is trying to say that I use for my rectangle like here, essentially, on the right side of it. But I still only want 5, so I only need 5 of them. And therefore, here we go. I got 1 times, again, the same width. But then I'm going to use these guys starting at the 0.8, the 75, the 65, the 61, and finally the 54. Okay. I'm not going to waste your time again. And we got a 3.35. Sweet. Okay. Last bit of this question, and I'll kind of explain a little bit more about it. So they have a multiple choice at the end about how is this integral of a prime set up. And you have to do a drop down. And you're going to say this is R5, and then this is an L5. And the reason why is because here we got a 3.35 versus a 3.77. So this is the lesser one, and this is the greater than one. That's all it is. So you're just picking whatever one was bigger and smaller, and that's it. There you go. So why is this applicable at all to you business people, right? I mean, it looks just like all the rest, and I get it. Think of it like this, where you have a whole bunch of like prices on a particular commodity, let's say, or some kind of product. And over time, you can see that the price is going up or down, something or so forth. And you need to find what the average would be. And so essentially what you're going to do here is take like the summation of it all, and you're going to divide it by n. So here in this case, it would be a 5, and then that's how you would find your average. But you can do other things with it. Maybe it's like total profit over time and all that kind of stuff. So each one of these would be like an individual profit, and you're trying to find it all out. But then over time, because I know here's a 1, but it could be like a 10, or it could be 100, or it could be 365, or it could be a 31, depending on time of dates and months and all that kind of stuff. So that's all pretty cool. The reason why you want to know about how to do it this way with these manual ones is because it will be discrete values that you have to work with. So say that you're taking stock market data, they're not going to say, oh, well, today's stock market went up by X cubed plus X squared minus 100 or something. No. They're going to give you these kind of numbers, and you have to then kind of calculate for yourself what you're expecting to gain or lose, or all this kind of stuff in the middle. Okay, so it's cool to be able to do calculus on this algebraic level, and that's what we're going to do here on the next section, which is really fun. It's super easy compared to this stuff. But in the real world, we're going to have these values that are kind of just like stuck, these like numbers, and you have to do something with them. What do? You add them all up and multiply. So there you go. All right, cool. That was my talk. And that's actually the last question of this section. So thank you very much, and have a great day.